I want to do something fun. I want to show that an example of it's not proving it's a conservative force, but show that the work done by gravity along two different paths is the same. So let me tell you where I'm going to go. I want to show that the work done for a ball moving down 2 meters and going along a curved path with this gravitational force is the same. And that doesn't prove it's conservative, but if they weren't the same, it'd prove it's not conservative. And what does conservative mean, and who cares? Just a brief review, because I want to get into the program in this, because that's really the fun part. We have the work energy theorem. This says the work done by some force is equal to the change in energy of the system. And we define work, it's actually an integral from point 1 to point 2 of f dot dr. And that's a path integral for a complicated situation, right? If it's a simple situation, we can do this, the work done by gravity along this path right here. Well, I can just take delta r, this whole thing, as a vector. Delta r, it's a constant. The gravitational force is constant. So I could say work, this is called this path 1. Work path 1 is going to be the force mg dot the displacement delta r. And I can write g as the vector 0, negative 9.8, 0. I could write delta r as 0, negative 2, 0. And so I can do this really easily. The work done would be the mass, and g dot delta r, they're both in the y direction. They're both constant. They're both negative. So I just get mg, let's just call this times 2. Let's say that's 2. And that's easy. Now, what about finding the work along this circular path right there? That's a little bit more difficult. I'm going to do it with Python, but it's not terribly difficult to do in Python. You could do it analytically, but then you have a problem, right? Because right here, I have delta r is dr is that way, and gravity is that way. Right here, they're in the same direction. And so you see, it's a difficult thing to do because it's a line integral over a vector field, which can get tricky, not impossible. And we do this in classical mechanics. But if you want to show that it's true for a situation for your introductory physics courses, we can do this in Python. Now, why do we care? Well, if you can show that the work does not depend on path, then you can move it to the other side of the equation to make it negative. And you can say the change in potential energy is negative the integral of f dot dr. And you can then, it doesn't matter what path you use. I can use this path. And that's how you get the change in potential energy is mg delta y. You know, delta y would be negative 2 here. So that's how that would work. So let's do this in Python. I'm going to start off. I'm going to have a ball move straight down. It doesn't have to fall. I don't really care about time. So I can just I'm actually going to break this into steps and move it down. And over each one of these steps, I can calculate the work. So d work will be f dot, I'll call it delta r. And so these are my delta r vectors like that. And then I just need to do the same thing up here along this path. Let's just jump into Python and do this because I know that's what I really want to do. And maybe you do too. So let's go over here and start up Python. I'm using Web VPython and Trinket. I'll give you a link to the code down below, and everyone will be happy. Make this bigger. That's good. Maybe a little bit bigger. Okay, that's good. Let's just start off with some constants. I definitely need g, the gravitational field, vector 0, negative 9.8, 0. I'm going to make a ball to move down. I'll call this ball 1 equals a sphere. I'm going to put it at y equals 1, and then I'm going to move it down to y equals negative 1. And you could pick whatever value you want. So the vector 0, 1, 0, radius of 0.1. You can pick whatever you want. Color, oh, not two of those. Color equals color dot cyan because it shows up well. And make trail equals true. I want to give it a mass. Ball1.m equals 0.1. I'm just picking stuff here. Picking stuff. Let's run it. I don't know why I want to run it, but I do. Let's see. Oh, there it is. There's my ball. Okay. Now I want to move down to my final position, so that's all I'm going to do right now, and then we'll calculate the work. dr equals vector. I just need to pick a value, 0, 0.010, and I'll subtract that. I should say negative, but I don't know. So while ball1.pos.y is greater than -1, I want to just do a rate statement so it animates just so we can see that. Rate, all I need to do is move the ball. So ball.pos equals ball.pos minus dr. I think that should work. Run it. And it didn't do anything. Oh, ball 1, that's why. Ball 1 minus dr, right. There we go. Okay, moving my ball down. Now all I need to do is calculate the work on that ball as it moves down. Let's call this work 1 equals 0. Now, I need to take f.dr, and that's my delta work, and add it to my total work. So work 1 equals work 1 plus the dot product m times ball1.m times g dr. That's not good. Because my d, let's make this negative, and let's make that plus. Right. So now I'm dotting them in the same direction. And remember, this should be a positive work done by gravity, because gravity's pulling in the same direction that it's moving. Then at the end, work equals, I got that already. Print it. Work 1 equals work 1 in joules. Now, I'm actually going to print out something else. Let's print out ball1.m times magnitude of g times 2. That, because it just making sure, just a double check that it's doing it right. I know that should be the work, mg delta y. So let's run that. Look at that moving down. Isn't that great? I should make it go faster. So the same thing. Got it. Now we need to do the second path, a curved path. Let's get rid of that. Don't need that. Let's make another ball. I'll do them one after the other. Let's make this rate 200 because it went too slow, and I'm an impatient person. Next ball, ball 2 equals sphere. Position is the same thing. Vector 0, 1, 0. Radius equals 0.1. Color is color.yellow. I find that the best colors for the default black background in Web VPython are cyan and yellow. Magenta works well too, but make trail equals true. Ball2.m equals 0.1. Okay, let me jump back over to the paper and show you how we're going to move this in a circle, and then we can calculate the work. How do we make this move in a circle? This is what I'm going to do. Here's the origin. Here's my ball up here, and I want to go like this. Like that. I can define this with a radius r and an angle theta. And then if I just change theta, then I can calculate the location of this each time. Let's say this is actually the vector, this is a radius r, but I'll call that the vector r, and that's the distance r. So the vector r will be r times cosine theta sine theta 0. So I can calculate that just by changing the value of r, theta. And I'll start with theta is pi over 2 because it's up here. And then d theta will be 0.01 or something. And then I just subtract that from theta until I get down here, which is while theta is greater than negative pi over 2. Now I do need to calculate this dr vector, or delta r if you want. How do you do that? Well, let's say it goes from here to there. and that's mostly a straight line, but this is the angle d theta. And I can use the arc length right there, so the magnitude of that dr would be r d theta. But I need the direction too. I need the direction of that vector. Here I can use a little trick. If I have the r vector right there, the z vector is this way, and r cross z would be that way. So this direction I can just put on here dr, and r, I'll call it r, that I can get rid of that, r cross z hat. So r cross z hat is going to give me the correct direction right there, and then I get the correct magnitude based on d theta and the direction based on this. It's a little bit of a trick, but it's fine. And I'll see if I can draw that arrow. Let's just make it move first, and then we'll go and see if we can add that arrow, and then we'll calculate the work. Back to the computer. There we go. Theta equals pi over 2. D theta, you got to spell it right. That seems a little small. D theta is 0.01, while theta is greater than negative pi over 2, rate 200. Maybe my rate's too fast. So the first thing I'm going to do is calculate the vector r. R is, I need r. R equals 1. R equals r times vector cosine theta sine theta 0. Now I'm going to put my ball there. Ball 2.pos equals r. Now I'm going to change the value of theta. So theta equals theta minus d theta. Let's run that and see what happens. And remember, I have that first ball moving first, and then it does the second ball. So first ball, second ball. That's awesome. I'm happy. Do you want me to put the dr vector? Let's try that. Dr arrow equals arrow. Let's call this d scale equals 1. I don't know. I'm going to have to change that. Position equals ball 2.pos. Axis, it's going to start off in the x direction. So let's say its axis is going to be equal to, I'm just starting off with this value, r times d theta times d scale, which I might need to change, times vector 1, 0, 0. Down here, I'm going to move that arrow. D arrow.pos equals ball 2.pos. And then D arrow.axis equals, I'm looking over here at my calculation, it's d theta times cross r z hat, which is vector 0, 0, 1. Oh, I need this d scale too. And I'm doing that just so I can change the size of that arrow to make sure it looks nice. Let's see if this works. Run it. And you don't need that arrow. And it did not work. D-scale is not a function because I didn't include the multiplication sign. Common mistake. D-scale, where'd I put it? D-scale right there, times. I could have done the same calculation for D-scale the first time I created it, but I didn't. I messed up again. No, can't find variable D arrow. What did I call it? DR arrow. DR arrow. Drarrow. Okay, so I think it's working. I think you just can't see it. So let's put this D scale at 100. Let's just see what happens. And let's move this up to 500 because I'm that impatient. Okay, So it's working. Let's make that a little bit smaller. How about 20? See what that looks like. But it is going in the right direction, and that's important. That's a little bit small, and I should stop here, but 40. Okay, that's good. Now I want to calculate the work. I know dr, I know the gravitational force. I just need to do the same thing as I did before. Let's make a work 2. Work 2 equals 0. If I want to add up a little piece of work, I have to have something to add it to. So you need this starting off with a 0 value. Before I move it, there's R. Let's just do it right here. Work 2 equals work 2 plus dot ball 2.m times g cross dr, which I did not calculate. Let's calculate dr. It's just this. This whole thing is dr. Oh, I did. Did I have a dr up here? I did. But it's fine. I can reuse it. And then I want to print that. Print work 2 equals, oh, there's extra space there. W2 joules. And I made a mistake. Right parentheses. Wow, I think I just copied and did not paste correctly. Line 29. Oh, I missed it right up here. Yep. I just didn't copy it when I didn't highlight the whole thing. There you go. So you'll notice that they're not the same. Why are they not the same? They're really, really, really close. Really close. They're not the same because I made some assumptions here, right? Every little step, I'm assuming that dr is constant. It's not. It's not a continuous curve. So this is the actual value. The other one's just an approximation. But the smaller your d theta step would be, the better it would be. So I'm pretty happy with this. It's a great practice at line integrals. It's a great way to practice showing that the work done is constant using a numerical calculation in Python. I'm pretty happy. Let's save this, and then I'll give you a link to this down below. 2-path work gravity is what I'm going to call it. I'll put a link to that down below, and I hope you enjoy that. That's the end.